Good morning, good afternoon, and good evening. Thank you for taking the time to join us today. My name is Ellen Carey, and it's my pleasure to moderate today's discussion hosted by proteanTecs on fail-safe electronics in automotive. I've spent my career at the forefront of technologies that are changing automotive and energy industries, leading key initiatives in electric and automated vehicles, as well as renewable energy for Samsung, Audi of America, and the American Clean Power Association. In my current capacity as Chief External Affairs Officer at Circulor, I collaborate with companies and policymakers on how technologies can create visibility and transparency within our most complex industrial and product value chains. Today, we have a great panel on fail-safe electronics for automotive, where we will be talking about fail-safe system architectures, the trade-offs between reliability, performance, and costs, and the use of silicon lifetime monitoring solutions. During the next hour, we will be talking with automotive SoC experts from CARIAD, Infineon, NXP, and proteanTecs. Before I invite our speakers onto the stage, a couple quick organizational elements. On the right side of the screen, you'll see the chat tab. Please submit your questions via that chat, and we'll address them in our Q&A session. Any questions we do not answer or we don't have enough time to answer will be replied to via email. If you have any technical issues, please use the same chat to send us a message. Our technical moderators will be happy to help. We'll take a few moments for each of the panelists to briefly introduce themselves and their role and what they're accomplishing. I'll kick off the conversation by asking some prepared questions, and then we'll open up the floor to give you an opportunity to engage in the discussion and ask your questions as well. Finally, we're recording this session, and this session will be sent to all registered attendees after the event. So with that, thank you again for spending your time with us. Welcome, and let's get started with introducing our panelists. First, I'd like to welcome Heinz Wagensonner. He's Senior SoC Designer for CARIAD Technology. Heinz, welcome on stage, and please tell us a little bit about yourself and your role.
I'm Senior SoC Architect at the Volkswagen daughter CARIAD, and I'm also the semiconductor quality lead in this company. I'm responsible basically for all semiconductors being used at CARIAD, and especially also the own developed SoCs like the AU1E multipurpose 7 nanometer SoC, which will be used in all future Volkswagen cars.
Awesome. Thanks very much, Heinz. It's a pleasure to have you here today. Next, our next panelist is Jens Rosenbusch, Senior Principal Engineer, SoC Safety Architecture at Infineon. Welcome, Jens, and please give us a little bit about your perspective and your role at Infineon.
Hello, everybody. Yeah, my name is Jens Rosenbusch. I'm working for Infineon already more than 20 years. And my current role is SoC Architect for Safety and Dependability, with here clear focus on automotive reliability, safety, dependability of our next generation microcontrollers, but also supporting, of course, our existing products.
Great. Thanks so much, Jens. Pleasure to have you here. Next, I'd like to invite Robert Jen onto the stage. Robert is Automotive SoC Safety Architect at NXP. Welcome, Robert.
Thank you, Ellen. Hello, everyone. Glad to be here. I have worked for NXP Semiconductor for more than 20 years now, and I'm based in Austin, Texas. I have held various roles in the company, and I'm currently working on the safety architecture definition of the latest generation of automotive microprocessor of the company. I'm also leading a few safety innovation initiatives within NXP. And one of those is enabling predictive maintenance for functional safety.
Wonderful. Thanks, Robert. Thanks for that perspective. And finally, rounding us out on our panelists here is Gal Carmel. Gal is Executive VP, General Manager and for Automotive at proteanTecs. Gal, over to you.
Hi guys, it's great to be here. So I'm Gal, I'm the VP and General Manager of Automotive at proteanTecs. proteanTecs supply health and performance visibility for advanced electronics. I'm a bit more than 20 years in the ADAS and automotive engineering. In my past, both Mobileye and Samsung, and it's great to see you all, especially during this sad time in Israel, and I'm happy that we can maintain technology and relationship with everyone, so it's a great panel.
Great. Gal, thank you so much. We have a lot to cover today, so we'll just get right into it. Heinz, I'd like to start with you, please. What do you see as the implications of fail-safe within semiconductor?
Actually, I will answer this question with a reply which I received when I was sitting on the other side of the table. I was working for 16 years for major tier one. And the Japanese customer asked me following question. He asked me, if you take your children in the morning to kindergarten, with which probability do you expect the braking system to work? Is it 100 ppm? Is it 10? Or is it 0? I think the answer is clear. That means fail-safe. Without proper fail-safe, we cannot sell any car on the market. So 0 ppm, 0 failures is clearly the strategy we have to go, especially when we think about autonomous driving. Autonomous driving is never going to work out without I would say, there is never 100% possibility, but 99.999999, we need to have a fail-safe system out there. Otherwise, people will not accept it. They will not buy it. And this has massive implications on the design of the semiconductors and the software.
Expound on that in terms of the design. So how do you see fail-safe having implications onto SoC design?
Well, if you had asked me some years ago, what do we need to do in order to have a proper fail-safe system? One of my replies would have been, we have to use an absolute rugged and robust technology node, for example. So the automotive industry in the past used quite old technology nodes, which were already 10 years in use by the consumer electronics. So this was one of our ways to evade, for example, problems with latent defects. But these times are over. So autonomous vehicles are never going to work out without latest technology nodes. We have to use 4 nanometer, 3 nanometer and below to make that work. There is no other chance. That means we are losing this possibility of being super robust by taking Stone Age technologies. And we can do this only if the design is getting much smarter. That means we cannot rely anymore simply on lessons learned from the past. We have to look ahead into the future. We have to measure the performance of the silicon in the field. And even before it comes into the field, we have to characterize it much deeper than we ever did it in the past. And this is the point. This is one of the cornerstones, one of the key enablers of all the nice things we plan to do in future, like autonomous driving, like having high performant computers on board, like also, let's say, dry braking systems, which you cannot do if the braking electronics is not 100% robust and reliable.
Great. Thank you. Thank you, Heinz. And I see nodding from Robert and from Jens. Jens, maybe over to you. Where do you see things in terms of what's needed and then what that enables in the future as well?
At first, I want to agree to what Heinz said. So the foundation of having fail-safe system is that the silicon has a certain robustness and reliability. And with this, we can then construct fail-safe systems which not rely on a single component, but maybe on different components in a car or on different parts of an SoC, which allow then, in case of one part is failing or is about to fail, that someone else can take over. And I think we see this fail-safe or fail-degraded systems more and more in the usage, especially in other systems. And I think this is the path for the future. Like Heinz said, we need to understand with modern technologies better what is the failure modes. We need to see how to react on changed mission profiles. Even if we look about software which is in the car for 20 years, this we will not see in future. We will see every few years or months or even weeks updates in the software, and with this, the mission profile of the silicon change. With this, the use cases change, maybe even the feature in the car change. And to be prepared for this, we need some platforms in the silicon, in the SoC, which allows to be extended in future, which allows to have redundant functionality, enough redundancy also for the future, enough headroom in our designs, and also some mitigation measures to detect whether some parts of the silicon gets burned out or gets overstressed, and react when with an update in the software or with an update in the usage of the silicon. And I think here we need some features in the silicon, some sensors, some detection capabilities to see several aspects of the silicon getting aged, getting degraded, and then react on this with an intelligent mechanism to allow the extended usage in the car.
Good. Gal, I know you have thoughts on this. So maybe round us out here on this topic of conversation. But then also I'd like to hear from you about the trade-offs between reliability, performance, and cost. So where do you see current and future technology and innovation going? And then how do we get there in terms of trade-offs and decision-making processes?
Yeah, so I think that the first thing that we need to understand is what trade-offs are we talking about? Okay, it's easy to talk about trade-offs, but at the end of the day, when you design a car, there is a cost implication, a performance implication, and a time implication. Okay, if we take a very complicated design that takes several years, but is not scalable, okay, maybe we got to a right performance envelope, but we've done nothing with that because we spent huge tons of money. So the first notion that we work by when we design a system is to first of all understand that the design trade-off must address changes over time. Okay, so it's not only that we close an SOP before production with a certain requirement and a spec. The spec change over time. Okay. Now we can divide it to external phenomena that affect this. For example, the requirements change over time due to the application and the workload. Application means that the software itself is changed due to training and inferencing and re-update itself, but it also has different workload. It uses the application, the detection differently in different places, in different domains, so it's fluctuating. Then we have environment changes over time. Temperature is different from different cars, different places. And then we have internal phenomena that we need to take under consideration. For example, each system starts with a different starting point, okay? And all of them is degraded over time, okay? So the performance and the mission profile is aged over time. And we need to take under consideration also software, things that are not crucial and critical, and they will pass and we can continue the maintenance of the system. So the first thing is to understand that we move from closing a spec in day 0 to update the spec and take the usage of data over time. Okay, so this is the first thing that we do in order to understand what the trade-off that we see. Now, let's look at a design. We have an example of a design. Let's look at the design of an SoC. If you can go to the next slide. So let's just a second understand the degrees of freedom that we have in the design. So if we take an SoC, we can break it to the main operation. On the left side, main operation is everything that the application by requirement needs to do and designed to do. And then we have the redundancy and the fail operation. Okay, so the redundancy and the fail operation has in between them a selector. The fail is a smart selector. Each one of us design it differently. It can be designed in different layers. But its target is basically to be smart when the system cannot perform, when it needs to fail safely, okay? Now, if we look at the redundancy part is also composed from things that we must do when we design. We have regulatory bodies and we have FMEDA and ISO that define exactly what we need to do. But on top of that, we have safety margin. Okay, each design takes different safety margin, and the first thing is that we need to visualize how much safety margin do we take. Okay, so now let's do a training of an agent. Okay, and the agent's job in this cycle is basically to balance in between safety and usefulness, but in a reliable way. Okay, right? We want to keep the reliability of the system, but we want over time to reduce power, okay, and to save money, okay. So if we design such agent, it needs to have a very unique phenomenon. First of all, it needs to have vertical detection. The reason is that problem can come from different places across the design, both in manufacturing and in the field, and from the system side or software side. So we need to be able to augment all of those. We need to track all of those phenomena over time to maintain tracking of all of those phenomena and to give context to the failure. If we cannot classify a failure and we don't see it in the field, then we cannot put a probability around it. Okay, so the next phase will be to create a model, a probability model around the failures. And we need to make sure that this agent is scalable, okay? Because at the end of the day, it's a function of statistical coverage. It needs to be able to hermetically close a core, but also a chip, and also to other chips, just based on the way that people implemented their failsafe. So if we take such approach, at the end of the day, the result is better prediction in high confidence. Okay, when we can characterize a problem, we can predict them better, and it opened the door to predictive maintenance. Once we have that established, we can start saving power and understand the trade-off better, because saving power can come from many places, from voltage, from frequency, from reducing the logic, from reducing the amount of power goes to those logic, and then we can better approach the KPIs and trade-off on the next design. Okay, so once we have those monitors and agents actively working in the field and correlating what we thought we're going to have to the actual field application that is utilizing the system, then we can be much smarter and implement things based on data, and over time reduce the amount of logic that is unnecessary, or do smart selection based on things that are fading and we cannot see them in day zero. So this is a way to visualize the trade-off in a physical design.
Thanks, Gal. Appreciate that. Robert, give us your thoughts on what Gal just talked us through and how you see the world.
Yeah. Thank you, Gail, for sharing your insights. At the NXP, we view reliability as one of the fundamental pillars ensuring vehicle safety, including functional safety. The core for reliability is multifold. The good reliability ensures a reasonable low base failure rate, which makes it possible for us to achieve the required safety metrics. At the same time, it helps improve the availability, which reduces the number of incidents and greatly improve user experience. With that being said, we do need to provide the needed performance at a reasonable cost so we can sell our products. Fortunately, in my limited experience, I have not seen the need to compromise on reliability or functional safety for performance gain or cost reduction. The automotive industry as a whole understands the importance of reliability or functional safety and is willing to accept the additional cost associated with that. That, however, does not mean that reliability, performance, and cost are always at odds with each other. One example would be the continuous in-field monitoring of the device's health status, which can give us great insight into minimum operating voltage or maximum operating frequency, which help boost the performance by either running faster or reducing the power consumption by lowering the supply voltage. The lifetime data can help close the loop for the reliability community to optimize the device model for reliability, which in turn also greatly reduce the cost of reliability testing.
Great. Thank you for that. So Heinz, over to you. Your thoughts on this, and also we could move into more of a conversation about the decoupling of hardware and software and how that is affecting the value chain.
So the automotive industry undergoes a complete transformation. I can share one short chart if possible. In the past, the OEMs earned money by selling cars and selling spare parts. So that was our business model over the past 135 years, I would say. That will all change with the battery electric vehicle. We all know the battery electric vehicle needs much less maintenance than an internal combustion engine car. This is one point. Another point is that these cars will be able to operate much longer. So we have strong indications that these cars will run without problems 500,000 miles. This is all achievable. So this business model will break down basically because if the car lasts longer, we will sell less cars and we will also sell less spare parts. So we have to find new possibilities, new income sources, and this is decoupling of hardware and software and selling additional functionalities over time via over-the-air updates. Could be that we add on new functionalities on hardware, which has the margin to run this code. It could be functions on demand. It could be data and e-commerce being run over the car. So basically the car will become a thing like a mobile phone. Or in other words, the future car is nothing else but a metal housing for the semiconductors inside, and the business model will be exactly the same like for mobile phones. And this is the way we have to transform us, which is not easy for the automotive industry because it's completely unknown territory for us. On the other hand, we have to make sure that all what we do here is safe and secure. And this is also a major challenge. If the cars are permanently connected to the internet, they are prone to hacking, malware attacks. So all of the things from which we were saved in the past, mostly saved, are now top important issues for us to be able to sell our products in future and to keep them safely operated in the field. Because nobody wants to have a hacked autonomous vehicle on the road. This is, I think, totally clear. I mean, that would be a perfect tool for ugly people.
Well, and in addition to being at an OEM, you were mentioning that you were in a tier one and other parts of the value chain before. So how do you see that this business change, dynamic change, affecting the whole value chain?
Well, actually, some people said, it will turn over everything. No, I don't think so. Because there will still be a lot of electronics where it is not so relevant to run own code inside. Let's take, for example, the braking system. I think CARIAD will never develop a braking system because we don't need to run own code inside, right? So we will develop the ECUs where we see value and where we get, let's say, most benefit for our customers, which is the high performance computing part and ADAS. So these ECUs will be overtaken by most OEMs on their own. Yeah, you can name them all. They will do this under their own flag. But still, there are going to be a lot of traditional ECUs coming from the old ecosystem. So I think there will be a coexistence between both models. And I mean, look at the explosion of code inside of a car. Look at the explosion of transistors needed to execute that code. Yeah. So that means for me basically only we are doing something more as add-on. So the complete, let's say, development effort is growing, and we will coexist with the traditional tier one. Yeah. So it's not our intention to eliminate the old grown ecosystem. Doesn't make sense.
Okay. Thanks for that perspective, Heinz. Very helpful. Robert, I'd now like to turn to you and ask you a question about what do you see as the challenges and new approaches around guaranteeing and extending mission profiles And how is NXP addressing new requirements?
Yeah, that is a great question. So there are a few major, or we call mega trends that NXP observed. I believe that you also observe the same mega trends: the autonomy, the electrification, and the connectivity. Those are what we see in the automotive world. All those which are driving a extended mission profile. I'll give you one example would be the central gateway controller. Then these to be connected to the cloud much longer than the traditional ECU that is only responsible for the steering system. Another example would be the autonomous driving. Imagine a fleet manager who is managing a fleet of robo-taxis. They probably want those vehicles to be driven on the road 24/7. And this poses great challenges for reliability and also safety. The traditional way to tackle these uncertainties brought up by the extended vision profile is we build margins everywhere. We build margins into our design, to our fabrication, into our test, into our reliability testing, qualification process. So we have margin everywhere. However, this can get very costly and to a point even unsustainable in the future. So at NXP, we believe a better solution exists in the near future. This is why we are driving the initiative with built-in health monitors or sensors to continually monitor the device health status. The data will be aggregated and analyzed, possibly through machine learning, to give us the insight we never had before. With this insight, we can decide to swap the device or ECUs before the imminent failures, which is what we call predictive maintenance, or limit the exposure of the device to a certain safety application, which is a dynamic reshuffling or reconfiguration of application tasks. NXP is not alone in this journey. The automotive industry has come together to define the framework of automotive predictive maintenance. And in last summer, in the past summer, we published a technical report we call TR9839, and which paved the way to the third edition of ISO 26262 standard. So GAIL and proteanTecs has done great work in providing solutions to enable this, and I believe GAIL has a lot to say about this.
Gal, would you like to chime in here on that third iteration of the standard on predictive maintenance and any perspective you see?
Yes, I think that Albert was spot on things that we need to do as an ecosystem. No vendor can apply such methodology by its own. The reason is that every vendor is responsible for a certain thing. At the end of the day, an OEM gets the entire thing packed inside the car, and he's the one that's responsible to maintain a platform. Now, we can work by every standard that we have so far, but we had a huge leap in technology in the last few years, majorly around software-defined, about AI and machine learning. And we differentiate in between what human can do and create rules at the beginning, and then software can update. Now, if we take that under consideration, we all understand that we need to work on those standards and to update those standards. Otherwise, we're wasting money. Okay, but every standard is statistical. At the end of the day, we need data, we need probability, and we need to be able to prove over time as a function of data that we have a point here. Okay, that we can observe the standard in a different way. In a different way, it means that at the end of the day, we found new advanced technologies in order to save power and cost. Okay, the power is a very sensitive creature inside the car. Heinz can reflect about it more than us. He builds a car at the end of the day. So working around the standards, working with the regulatory body, working as an ecosystem, writing white papers, and applying mathematical methods to collect data and prove points in order to regulate them, this is the only way that we can, at the end of the day, standardize those procedures. So I fully agree with what was saying here.
Yeah. Great. Great, thank you. From my perspective, couldn't agree more. It's very important that technology and business and regulatory standard setting bodies come together and have that discussion to continue to track towards the state of the art and what actually achieves the mutually and collective goals. Jens, I would like to shift gears a little bit here and kick a question over to you, please, specifically on power and power strategies. So what do you see as new technologies for power strategies in the field, please? Would love your perspective on that.
Mm-hmm. Yeah, as we heard from Gal already, power is a very sensitive topic in the automotive industry. So in the past, it was about you have a 12-volt battery, and if you are on standby, then this battery should not be leaked out by all the silicon which is still active. And you may ask, okay, in future we have battery electric vehicles with huge high voltage batteries. But on the same side, we have also extended usage of microcontrollers or silicon in the car. So it's getting more and more ECUs. And we have also the problem that if you draw too much current from this battery, you don't have this current to drive the car. So it's basically every current you draw for maintaining your silicon is reducing your range of the vehicle. So it is still, or it's continues being a very important parameter to save power. And what can we do now? So we, as I said, we have more and more silicon in the car, and each of these silicon has a function, but not all of these functions are needed at the same time. So one of the major techniques to save power is to switch off everything you don't need. And so you can say, okay, this starts with an ECU. If I have a steering ECU, but the car is parked, I don't need it, I can switch it off. So it is starting with a power system in the car where you can decide which of the electronic components is powered at all. But it's also going down into the SoC. So if you have one SoC, which is, for instance, used as a gateway and in parallel doing some support functions or maybe some infotainment or whatever, then also these functions are not all in parallel needed at the same time. So also on the SoC, you have the same thing like you have on car level. You have in a smaller portion also an SoC. Not everything has to be powered at the same time. So you can also have power domains in your SoC and define which of the power domains is active at which time. So having an adaptive power profile according to the mission you currently execute. Yeah, parking is different when driving, charging is different when driving, and so on. You can make this very adaptive. And on top of this, modern power saving technologies can also come into the game. So with our new technologies, the leakage of the silicon is getting more and more portions of the total power consumption of a silicon. So in the past it was more like active current, now it's more leakage. So you try to minimize the leakage in your design, and there are several techniques. And one of the techniques is that you, for instance, scale dynamically your voltage. You can trade between low power, low performance, and on the other hand, high power and high performance, and can adapt in this way also with the same functionality what amount of power you currently need to perform your needed task. So if you drive, let's say, if you drive faster, maybe you need more processing power in your other system because you need to react faster. This you can scale. Or if you say you have several redundant options in your silicon, where you say in one use case I operate on the one path, and in another use case I operate on another path, when you can switch also here the voltage between an high performance mode and a low performance mode. So in this sense, the complete power system is hierarchically in the car. You define for which functionality of the car you need which ECU. You define on the SoC level which functionality of the SoC needs to be powered at the same time. And you define even lower granular on each functionality level, which dedicated part of the silicon needs which power performance portfolio at a certain time. So with this, you make it also very, let's say, difficult or complicated to find out whether your mission profile, your expected aging profile of your silicon is currently held correctly consistent within your SoC, since you don't know at the time you build an SoC what later on in the application is really used. And of course, you can say, I build a system which is robust against the worst case, but this is when, of course, very expensive and needs a lot of power. So what we need is flexible designs which can scale the current operation between performance modes and power saving modes, and where you also can monitor what is the current aging budget you have consumed with a certain silicon part. So if you have a silicon part in a high performance mode with higher voltage supply, then it is aging much faster compared to if you have it in a low performance mode with low leakage and low performance. And so you need to keep track on what is the aging profile, let's say it this way, of your silicon, and whether with one part of the silicon you come to a border where you say, I better not use it anymore in the high performance mode. And this now, to close the circle here, this comes then back to what is my prediction on the remaining lifetime of my silicon, or of a function in my silicon, and what is my measure, my fallback measure, if this is a safety function, if I cannot use it anymore, or at least I cannot use it anymore until maintenance. So when I need a fail-safe system where I can go into a degraded mode, which is using then a part of the silicon which is maybe not aged so much, and where I can survive my critical functionality driving, let's say, until I have a maintenance. So, and I think here this is exactly what this talk is about. We need this health state management. We need to monitor what is the current life state or health state of a silicon or part of a silicon, to decide on a clever strategy to extend the usage of the silicon until I either have completely worn it out, or either I have it replaced by a spare part.
So nicely said, Jens. Thank you for that. That was really a great explanation. I also was thinking about Robert's, the drivers behind automotive right now on, safety and autonomous and more digital and everything. And it really seems that this power strategy management is really key to making all of those pillars happen. So that was one of my key takeaways. Robert, over to you. Wanted to ask you a question about how new technology innovations are affecting companies' business models. Can you share with us what you're seeing there?
Sure. This obviously is a big question for me to take, but I will try. So I believe major technology innovation will most certainly have a significant impact on how the companies operate, including their business models. I would still like to use predictive maintenance as an example. So we all know one of the bottlenecks to enable predictive maintenance today is a lack of data sharing between stakeholders. NXP, as a semiconductor vendor, we do not have access to the user data, the in-field silicon data. We have to rely on our ecosystem partner, in our case, OEMs, to relay that data back to us. And we all know that data is a new oil in this era. So no one is willing to give the data for free. So that's why we need to come together somehow to define the framework of the data sharing and to make sure that everyone is a winner, including the final consumers. So this is a great challenge to our current business model. I cannot say that we already solved this challenge yet, but I think this is a great opportunity for us to come together to brainstorm how we can do that together.
Helpful. Yeah, I see that in my work as well in terms of sharing data and creating technical standards for that interoperability of data, which is really the next era, as we say, in terms of collaboration and collective success. I wanted to turn to Heinz, please, now. Heinz, tell us a little bit on your perspective, please, on chip-based architectures and how chiplet-based architectures are impacting industry roadmaps. How do you see that when you look into your crystal ball?
Yeah. Chiplets are on our radar in the automotive industry, definitely for several reasons, several good reasons. One reason is that due to the performance explosion, or let's say the demand for performance, it's going to become difficult to cover that with monolithic SoCs. The monolithic SoCs would become larger and larger and larger, and if they grow large, the yield will go down, the costs thus will go up, and the failure probability will rise, as you always have the risk of latent defects on large area chips. Yeah. So it absolutely makes sense to decompose monolithic chips into functions and function blocks, to segregate them and to assemble them as you want them to have. This is one thing. The other thing is the design costs for advanced nodes are meanwhile so high. We are talking about billions of dollars for advanced node SoCs, that it makes sense to change only the functions which give you the most benefit. That means, let's take the compute core. Yeah, you have quick advances in the compute cores. You also benefit a lot by using new technology nodes like 3 nanometer, 2 nanometer and below. Then it makes sense to change the compute core and only the compute core. But do you need to change, for example, the interfaces, the PHYs, the memory, the power supply? Eventually not. So you can keep those as they are, and you just change your compute block, your compute chiplet. That gives you many advantages. First of all, it speeds up your development. Secondly, it reduces the costs. And thirdly, you improve the overall reliability because you have smaller dies which inherently have a higher yield and a higher reliability. But this all sounds nice, but it comes also with some challenges. At the moment, we don't actually know, we have no idea how to build a chiplet for the automotive industry which can sustain temperature changes like we have it in the car, humidity and vibration. The chiplets being used up to now are being used in data centers where you have more than stable conditions. So which chiplet technology, which assembly technology might be able to perform 15 years without failure in the field, we don't know yet. So this is a big field of research where we have to step in. The IMEC at the moment is building a consortium here to work on that. But secondly, if we look at it, you always will have thousands over thousands of ultra-fine interconnects. And those cannot be inspected with traditional methods. You cannot inspect them electrically, you cannot inspect them with X-ray, not with ultrasonic. So whatever you do, you have a lot of hidden interfaces where you have no chance to check if at time zero they are without latent defect. And that is a great opportunity for on-chip sensors, because they can be attached directly at these interfaces. They can monitor in field the behavior of the interfaces. And if one interface, if the communication AI is getting smaller and smaller, you can warn the driver, you can safe shut down the system, you can even switch to redundant lines. So we get a lot of possibilities due to on-chip monitors. For me, they are a key enabler for using chiplets in the automotive industry, however these chiplets might look like. My personal opinion is we won't see it in this decade, but early of next decade, I think we are going to see chiplets in the car, and then for sure with on-chip monitors.
I'll add to that. It's a very nice answer, but I'll add to that at the end of the day, even if you succeed to accomplish a very good design, and you want to create a platform out of that, a scalable platform, and you want to change only specific things inside the chiplet, you need to create a bit exact process that say, okay, the things that I haven't changed, are still working properly. Let's just handle the things that I'm changing over time. Otherwise, the overhead of the redesigning of such platform just doesn't make sense. So the entire methodology about releasing, about SOP-driven approach, and how you build system needs different thinking when you deal with such complicated systems. So I fully agree.
Interesting. Fascinating. Thanks for that to you both. We unfortunately have time for one question left, and back onto predictive maintenance and monitoring and the importance, and looking less into the future and more into right here and right now. What is needed today in terms of providing monitoring and that predictive maintenance? So, Jens, why don't you kick us off on and share your thoughts?
So I think we have set the stage for this last question very nicely. We heard already many times that it starts all with understanding the current system state. So we need monitors. We need to observe what is the silicon doing right now, in which operating condition it is. Is it aging? Is it still within its mission profile? So we need to first understand, do we see the correct operating of the silicon? Is this silicon in a healthy state? Is it operated at a healthy environment condition, like also heat and vibration and whatever, yeah, voltage? And a second thing is then what to do with this knowledge about the silicon state. So we need sensors, and we need to deal with the outcome of the sensors and make something out of it, which is beyond just looking at is a temperature within a certain range. But as we have heard already, it's about combining these different silicon information or KPIs into something which represents an age or a health state of a silicon, of a function on a silicon, and then predict what is the next step to do. It could be, for instance, with temperature, we typically switch off functions or reduce the performance need for the function so that the silicon can cool down. This we do today, and this is then also done in the future, even more granular, more fine granular. And if we think about using also AI for analyzing effects which we don't know as a human, yeah, but the AI can see a pattern in a certain behavior of a silicon which we, with our traditional statistical methods, not easily accessible. We heard also, I think this is true for the silicon vendors, that we have no insight into what is really done in the car. So the OEM may see it. So the OEM may have access to sensor data in the application runtime where the silicon manufacturer don't have. So we need to have here a cooperation that we also feedback the insight into what is critical parameters on the silicon, to what is the behavior in the field, to statistic of big data in the car fleet, which of the data lead to an excursion, so there's some silicon behaving strange, so we can detect this. And we need to do this while the car is on the road, and not like we do it today, when a failing part comes back to the silicon vendor, where we analyze it and look, okay, what happens 15 years back in my production? So this, I think we don't have the time for this. We need to look the operation of the silicon while it is in application, while it's executing, and we need to draw conclusions during the runtime of the car and react on this with either changing the operating mode of the silicon, making a software update, or bring it back into maintenance state.
Very well said. Thank you, Jens. Very well said. Very helpful. Gal, close us out here. What you see is needed today in terms of predictive maintenance and monitoring, please.
So I think each and every one of us touched it from a different perspective. That leads me to the fact that we need a change of thinking. At the end of the day, all of us as engineers can pre-design and create rules and thresholds and algorithms that explain data and create an init state of a system. But the software plays a huge role with its ability to, design and memorize data, interpolate and extrapolate, and then generalize. And it's a huge tool that can continue the work of that we've done on the engineering level in the field. But then we need to deal with phenomenon that must have hardware mechanism because we need to react very fast to things that happens on a silicon level, like V-drop, for example. Voltage is dropping very fast. So the change of thinking that we need to do is to embrace a vertical thinking. Embrace a vertical thinking, it means that we understand the supply chain. It means that if we can utilize and understanding the supply chain, we can create clear targets and clear KPI. Work by data-driven approach, deep data-driven approach, when we create a common language. Pull out the insight that we need over time, create the right prediction and right mechanism, and create a full loop in between design, which is a cross-platform thinking. Today, each group is thinking separately on a subsystem, but at the end of the day, we need to scale. We need to create something, even if it will cost a lot of money at the beginning. Like every evolution of technology, we need to build the infrastructure in order to be flexible enough to design on top of that. So we cannot avoid hardware mechanism. We need them in certain places to do something. Then we need to utilize the advantage of software collecting data. And we need to physically analyze it also by hand to create rules around it and to create the right guard. This change of thinking in between the industry can lead to both cost reduction, time efficiency, and better product at the end of the day. We're selling cars, okay? We're building cars. So yeah, so I think that will be the main thing that I will put as an emphasis of what I think should be the approach in order to drive a change, to drive a vector of a thinking change.
Super. Thank you for that. And that creates a great segue into our Q&A and our discussion and engagement with the audience. So if you have questions, please enter them into the chat now. We've got a number of them coming through. And so let's turn to the audience and see what's on their minds. Okay. Great. So looking over the questions from our audience, everyone, we had a question on AI, Jens. You mentioned AI and its potential, especially in analysis of the data and what's going on within these chips. So tell us in terms of how you see AI coming into that analysis and what are the opportunities, please?
Yeah, looking like we use today AI in our production processes to optimize production steps, to also optimize the test programs which operate in the silicon vendor production. When we see that the AI allows us to see statistical effects which we hardly can see with other means, so it allows us to better find out which of the devices we have produced are really good, which can be shipped so that we not throw away good dies. And it also allows us to see much better than with other methods whether there is a hidden problem, a latent fault somehow hidden in something which is not obvious on one parameter, but maybe on a combination of several things, which for a human brain is hard to find. So today we use AI to find the unknown, to really see pattern in things, in statistical data, which we are hard to grab by ourselves. And if we now would use such, let's say, analysis methods, not only in production, but also in the field, so really allow us to look on the silicon behavior while the car is driving, while it's operating out there, and have then statistic not only from one car, but from million cars in a fleet, when we could use these AI mechanisms, this analysis to find latent fails in the field. We can find production excursions which are out in the field, which we could not see before. And for this, we need, of course, the sensor data. We need an infrastructure to accumulate the sensor data in databases over a complete car fleet, and then allow in this, let's say, cloud processing, wherever it is, to find out statistical anomalies and react on this with a software update or with a callback of potentially wrong devices from the field. Yeah? And this much earlier than it is today when an OEM sends back the data, the broken ECUs to a tier 1, and he sends back an MCU to the tier 2 to do failure analysis and find bugs which we have implemented 10 years back. So we don't have this time in future.
Robert, would you like to respond to this audience question as well?
Sure. Yeah, I completely support what Jans just said on the opportunity to apply AI into the anomaly detection, predictive maintenance. I want to bring that perspective back in the standardization. So we know that AI is still a maturing field, and there is a concern with using AI that could lead to some inaccuracies. And that inaccuracy would lead to false positive or false negative. And that comes into how do we tackle these false positive or false negatives into predictive maintenance in claiming either predictive mechanism as safety mechanism to detect latent fault, or in using that to predict the remaining useful life. How accurate we need AI to be to give us that prediction. I think that is still a very interesting topic for us to develop and define, or maybe we can have that in the standardization framework to give a guidance to the whole industry.
Great. Thanks, Robert. So we have another question from the chat, and this one is specifically for Heinz. And it says, what is the current state of processes for the industry in terms of failure analysis? What does that look like now so that we can understand where we're maturing from?
Mm-hmm. So when I was responsible for failure analysis at the tier 1, it bugged me because it was a very, very slow process and a brittle chain. Yeah, so a car is failing in the field, the ECU has a failure, it's taken to the workshop. Already here, you lose time. The workshop is taking out the ECU. The failure description is typically poor because in the workshops, they don't have electronic experts. They have really a hard time to interpret failure codes. And therefore, you get at the tier 1, the ECU with almost zero failure description. Yeah. Most of the times, the failure description is warning lamp was on. And then you have to reproduce the failure in your laboratory, which is an artificial environment because you're not in the car anymore. So here already there's a high chance to lose the original failure. Eventually you are successful and you manage the failure reproduction. And then the next step is to isolate the failure inside of the ECU. Which component is causing the failure? And let's assume it's the SoC in the ECU, the microcontroller, for example. So after days of failure analysis, you localized it's in the microcontroller. The clock is meanwhile ticking because you are obliged by your customer to provide a complete AD report, including the countermeasure and the risk assessment within 30 days. So you analyze under high pressure, day and night. So you isolate the problem, let's say the microcontroller. You desolder it because only a desoldered microcontroller can be analyzed from the tier 2, from the semiconductor manufacturer. Again, high risk to lose the failure because you apply high thermal stress on a component which is anyway not properly working anymore. Then you send it back to the tier 2, and the tier 2 has exactly the same problem. So the tier 2 is receiving only the microcontroller and has to reproduce the failure in his artificial condition environment, which is a so-called ATE tester, a production tester running a production test software. And this software has nothing to do with the software which was executed in the car. So again, they try to reproduce the failure. They lose days, sometimes weeks, until this works out, because without reproduction, you don't know where to look in the silicon, where might be the problem. You have to reproduce it, then you can localize. Without that, zero success rate. And if we look at complex SoCs, this process can last months, many months, because the silicon is so complex and the problem might be so specific that it is very complicated, and own software has eventually to be developed to trigger the failure. So it's really harsh. However, if you don't isolate the failure, you ship out parts into the field, affected parts probably, millions over millions. And we cannot afford that anymore in future. So as of now, we are stupid and we are slow. And for the future, for autonomous vehicles, we don't have this time anymore. Now, if you ask me what was my favorite customer to launch new SoCs, I can tell you it was always the most failure sensitive customer. There are customers which are more failure sensitive and others are not so sensitive. But when I had to launch a new SoC, I was always talking to the management, hey, let's do it with the most skeptical customer because they will send back immediately failing parts and I can debug them. So I get immediate the chance to debug the SoC before we go into mass volume production. If you do that with an OEM which is not so failure sensitive, you shoot out parts and fill the field with faulty components, and that will kill you when you are in large volumes. And now with the on-chip monitoring, we have the great chance. In best case, imagine we don't even need to send back the ECU because we are so smart that in real time we see what is wrong. And we can react on that even without having hands on the ECU.
I think that's an excellent current state, future state, where we're heading, what's enabled, where the innovation is taking us. I think that that really leaves our audience with something to think about going forward, Heinz. So thank you very much for sharing that perspective. That's great. And with that concludes the end of our webinar. Thank you to the audience for joining. Thank you for our panelists here from CARIAD, from Infineon, from NXP, and from proteanTecs for sharing their perspectives from their parts of the value chain and what where we're headed in terms of fail-safe architectures and possibilities. So thank you.
Thank you.
Thank you very much.
Have a good evening.
Thank you very much.
Bye-bye.